Temperature, top P, top K, you've seen these settings. Maybe you've been just copy pasting them and hoping that it will work. Here's the thing, they are all the same knob. And today I'm going to explain what is this knob and dive deep in all of these settings. An LLM doesn't output words, it outputs scores for every token in its vocabulary. Then those scores are converted into probabilities, and then exactly one token based on the probabilities is going to be picked. And all the settings that we just saw on the list are rules on how to make this one pick. Okay, before we dive in, I want to give you a simplified mental model on what an LLM actually is. So, at its very base, any model is just a combination of two components. The first one is the architecture. So you can think of it as of the brain of the model. Okay, so this is a set of hard-coded rules that the vendor of the model puts inside. And then we have parameters, and these may sound oversimplified, but it is true. Parameters are nothing but numbers, billions of them. We have embedding numbers, we have the attention matrices, we have the feed-forward network numbers, normalization, and so on and so forth, a lot of them. And when a model is worked, the brain works its neurons. Okay, it transforms them, it moves them around, it gives them weight, takes weight from them, um, and so on and so forth. If you are unfamiliar with these concepts, with layers, attention, with embeddings, that's okay. You will still understand this video on the high level. But if you want to learn more, you can check my other videos or use any other source that you'd like. So, operations are applied to numbers, and there are many of them at many different levels, many different operations. They all work together to consequently work out the magic of generating a text for you. But today we are interested in one of the last stages of this process, which is the inference. Okay, so we need to first try to understand what an LLM's vocabulary is. A vocabulary is a set of tokens which defines what the model can read and write. And that means that if the token, let's say token A or its byte equivalent, they are not present in the vocabulary for some reason, then the model will not be able to read and write it. That's why you may have seen the older models outputting this generic unknown symbol when they didn't have the token. Of course, you will not see the modern models doing this. And that is why the vocabulary is built before the main training. A sample of the training data is passed into the tokenizer, which then builds the vocabulary. Now, there are many different algorithms for this, but the famous one is the byte pair encoding. It is used, for example, in GPT models, which repeatedly merges most frequent pairs of tokens into new tokens. So, when a prompt comes in, the model scores every token in its vocabulary, all of them. These scores are called logits, and the higher the score, the more relative to the context the token is. Then a softmax function, which is just a mathematical function for converting logits into probabilities, does its job and creates these vocabulary probabilities. And then at random, a token will be selected. But of course, tokens with higher score have more chances of being selected. Then the selected token goes into the output. Okay, so now I'm going to explain the softmax function. If you are not interested in formulas, you can just skip ahead a little bit, but this one is really simple, so I decided to add it here. Let us now try to understand the variables of this formula. First one, Z, is our logit, the raw score that the model gave us. But since the model produces unbounded numbers, we have a problem because the score can be negative. And of course, we can't use a negative number in a probability. That would make no sense. So we need a clever solution which will both make the number positive and also preserve the ranking, the relative order that the model gave us. So the best solution that the mathematicians have found is to use an exponential function, because every positive number taken into the power of any other real number will produce a new positive number. And of course, this multiplying that we do will also preserve the ranking of the scores. Now, the score of this token I that we have over here is guaranteed to be a positive number, but we are not done yet. We need to take one more step, because probability answers the question of what are the chances of picking this individual token I from the pool of all tokens from our vocabulary. And in order to answer that question, we need to divide the score of this token I by the sum of all the scores that we have. If you are unfamiliar with this is the Greek letter sigma, and it represents the operation of summation over a given range. So we divide the score of our token I by the sum of all scores, and that's it. That's it. And we get our probability, which is a number from 0 to 1. This is literally how the softmax function works. Well, we are done with the hard part. We know that the model produces raw scores, that these scores get converted by the softmax function into probabilities, and we know that the token with a higher probability has a higher chance of being selected and added in the output. But now let us try to understand how different settings that we pass to the model affect this selection. Okay, the first settings that we're going to discuss is the temperature. It's super easy because its operation is just a basic division. We just take the logit, the score for a token, and divide it by the given value of the temperature. Now, you may have already seen that the common range of temperatures that the popular models allow is from 0 to 2. Now, when we pass 0 as a temperature, of course, it doesn't divide the score by 0. It just treats this as a special command to find the token with the highest score and just select it no matter what. Then we have lower values of t. We use them when we want the model's output to be super predictable, because as you can see, it sharpens the difference between the scores. And the favorite score, for example, the math over here, which had the greatest value in the list already, gets even bigger. Okay, we divide 3.2 by 0.2, and we get 16, which, as you can see from this pool of tokens, gets super high probability. Then if we want to just rely on the model's output, we pass 1, because nothing will change in the score list. The scores will just get divided by 1 and nothing will change. And if we want the model to be quote-unquote creative, we in that case we want to flatten the list, and we pass a higher value of t. Okay, now let's see how this range works on an example. So I passed this prompt to a Qwen 2.5 base model. We can see that at t equals 0, the output is boring and predictable, because only the tokens which the model has ranked higher are being selected. Then at t equals 0.7, we have an answer which is varied but wandering. And the most interesting part is when we pass a really high temperature value like 1.8, because as you can see, the answer is some gibberish. Now, since we have flattened the list, we have increased the chances of some junk token to be selected, And once it is selected, everything else then is built from it. It compounds. Okay, the next setting is top K, even simpler. We just tell it to keep its top K candidates and delete everything else. But of course, this has one huge flaw because it is blind to context. How do we know that the model is that sure about them or if the model is completely torn? Okay, the problem of this cut is that it never adapts. Next, top P. This one is smarter than top K, though they are conceptually similar, but the difference is that top P reads the room, it solves the confidence problem. We say it keep collecting top options until their cumulative probability, the sum of their probabilities, uh, is equal to the specified value, for example, 90%. This way, it doesn't matter if the model is confident and the distribution is sharp, or the model is torn apart and the distribution is flat, because we will still collect the required probability mass. Another setting to control the model's output is stopping. We have two options here. The first parameter is max tokens. Now, the problem is that it will stop output once it has reached the specified number of tokens, for example, 16. And because of that, this can happen mid-sentence. That's why this is used mostly as a strict cost control tool, budget control tool. For the graceful stopping of the output, you'd rather use the stop sequence, which will stop the output once the specified token has been produced. Okay, so what if you want to receive the same answer every time you pass exactly the same prompt? Now, because of what we have discussed previously about temperature and the case where t equals 0, you might be tempted to think that this is your solution, but it is not because of the other sources of non-determinism. The solution here is to use a special parameter called seed number. By passing the same seed number with the same prompt, you can achieve this, but keep in mind that even this doesn't guarantee you a 100% likeliness every time. So, and the final piece, the logprobs, you can request them to be included in the model's output. And this is just a way to pick into that list of probabilities that we have been discussing all along today. This is helpful when debugging, when building classifiers, and when grading the model's answers. So I hope this was helpful. That's it for today. See you next time.